Hi, my name is Matthew Payne. In my day job, I'm the acting director of the Minor Planet Center, but today I want to talk to you about another project that I've got on the go with Mike Alexanderson and Matt Holman, in which we're using TESS data to search for faint, distant, outer solar system objects using the shift and stack technique.
Okay, to orient the rest of the talk, I'm going to start by giving a brief overview of the outer solar system. So in this plot of eccentricity versus semi-major axis, you can see Neptune at 30 AU. Heading inside of that, we have the other giant planets, Uranus, and then there will be Saturn and Jupiter. Then heading out from Neptune, we have the Kuiper Belt region, sort of spreading out over sort of a region around about 40 to 50 AU. We have these scattered disk objects whose pericenter comes into around about that Kuiper Belt region, but they have much higher eccentricities. Then we have centaurs, which have a similar eccentricity distribution to the scattered disk objects, but their pericenters come inside the giant planet region, so they're crossing orbits with Neptune, Uranus, etc. Moving further out, there are some objects which are slightly detached from the scattered disk distribution, such as Sedna. There are then sort of hypothesized objects, such as Planet 9, which might exist with a few hundred AU intermediate eccentricities. And then there are much better characterized, differently existing objects, such as comets, which have orbits with semi-major axes of many thousands or tens of thousands of AU and eccentricities asymptotically approaching 1. So these are the semi-major axes and eccentricities of the objects that I'm going to be sort of talking about during the rest of the talk. And to give you some understanding of the magnitude distribution of the objects that we currently know about, that we're going to be trying to find, the Kuiper Belt objects that we currently know about have a magnitude distribution as plotted here. For reasons that will become apparent in the rest of the lecture, some magnitude around about 22nd magnitude is going to be of interest. So currently we know of about 1200 such Kuiper Belt objects that are 22nd magnitude or brighter. And for those centaurs and scattered disk objects with a much higher eccentricities, again at that 22nd magnitude range, we have around about 800 are currently known at that magnitude or brighter. So the rest of this talk is going to be trying to describe how I'm working with Matt Holman and Mike Alexanderson on an ongoing TESS project to search for new distant solar system objects using TESS data. So the rest of this talk is going to be going through how we are actually going to do that using current and future TESS data. I'm now going to give a brief overview of the shift and stack technique, which is the main method by which we can use TESS data to discover faint, new outer solar system objects. So going back about 20 years, here we have a bunch of exposures that were taken by Gladman et al. Using CFHT. And each of the individual exposures here has been shifted relative to one another. And the shift that's been employed is by an amount that's appropriate to account for the motion of a Kuiper Belt object in a circular orbit at around about 40 AU. And you can see that when you do those shifts and accumulate all of the flux together, the images of the stars get smeared out in the direction of that shift that you've applied. Whereas the 1, 2, 3, 4 Kuiper Belt objects that are in this image get nice, sharp, crisp images in which all of the flux stays in a nice compact region. And that's fundamentally the essence of this shifting and stacking technique. Now, as well as this shifting and stacking up of the flux in one area, you can do a few other things that are of interest. One thing I'll mention briefly is the ability to look at faint objects that you might otherwise naively expect to be hidden in the glare of bright objects. So here's some more CFHT data, zooming in on a 14th magnitude star in that image, and then again shifting the data at a rate appropriate for a Kuiper Belt object. Now we're going to take the median of each of those images and subtract it from each of those exposures. And so now when we look at this, the shifted median subtracted data, most of the stellar flux has disappeared, leaving a 24th magnitude object easily visible that would otherwise have been totally overwhelmed by this flux from the 14th magnitude star. In addition, you can do more complicated shifts. Previously, I discussed shifting things along heliocentric orbits to account for the motion of, say, the Kuiper Belt object. But here, Holman et al. Did a sort of more complicated, sort of effectively a helical shift to account for the heliocentric motion of Neptune, and then in addition, the motion of a satellite going around Neptune. So when you shift and stack the flux on that more complicated trajectory, that allows you, in this case, to discover many new moons around Neptune. And then finally, another example is a study using the HST ACS instrument led by Bernstein. And in this study, HST's single exposure limit was around about 27.6. Bernstein et al. Took around about 50 exposures, allowing them to get down to below 29th magnitude. When they did this, in their field of view, they deliberately had one known 23rd magnitude object, and they then discovered 3 new objects. Now, discovering 3 new objects sounds a bit so-so, but the crucial thing to understand here was that based on the size distribution that was known at the time, they actually would have expected to discover 80 new objects. They discovered 3, and so this was the first confirmation that there was a break in the size distribution at around 25th, 26th, 27th magnitude. Now, this study by Bernstein actually provides a lot of the machinery to illustrate the approach that we are going to take with the TESS data. And so I'm going to refer back to this study a few times when estimating the number of computations that need to be performed and the expected scientific results that will come out of the TESS study. Okay, so we want to perform a blind search for unknown outer solar system objects using TESS data. So let's consider how we're going to do that. So if we had a known object, it's easy to imagine how to use shift and stack. You've got a known object with a known orbit, you know its position as a function of time, so you know where it's going to be in each exposure, so you can work out what the required pixel shift is between each exposure to do the shift and stack. Now, for an unknown object, it's a bit harder. The unknown object could have unknown orbit, could start anywhere in or off the field of view, could be moving in any direction, could have almost any rate of motion. And so, in order to recover, find, search for a whole range of objects with a whole range of possible orbits, you're going to have to search a very large parameter space of different orbits. And it is clear that some of the sets of parameters you choose are likely to be more successful than others. So in this CFHT example I showed before, the authors are just searching for motion parallel to the ecliptic, and that yields great results very quickly because there's a lot of objects in the Kuiper Belt moving parallel to the ecliptic. But if we want to exhaustively search for unusual objects moving on unusual paths, then we have to search through a vast range of parameter space. So one of the key tasks here is to think about what do we need to search, like how many different discrete orbits is it worth searching. So let's think about one particular orbit that we might search. So an object with that orbit is going to be executing Keplerian motion, and so we know where it will appear as a function of time because we can extrapolate Keplerian motion forward. So that's great. So we know where it's going to be. Now, it turns out to be useful, even though it's executing Keplerian motion, not to think of Keplerian coordinates or even like really Cartesian coordinates. It's actually sort of useful to parameterize the orbits in terms of like some angular variables that give you the starting position of that object with respect to your first exposure. And so here we're taking the Cartesian x, y, z components and turning them into some alpha, beta, gamma angular components. Okay, and one of the reasons for doing this is it sort of helps us to think about what sets of orbits are worth thinking about. And the idea is that we really just want to consider discrete starting positions, effectively one starting position per pixel in the image. And then for the angular rates of motion, again, we just want to chop them up and just consider rates of motion that will move us from one particular pixel in exposure 1 into a different pixel in exposure 2 and 3 and so on. So we don't need to consider all possible angular rates of motion, just ones that move as discrete numbers of pixels in each direction. Okay, so then we can say, all right, that would be what our starting conditions would be. So what is the observed position theta going to be as a function of time? Okay, well, we can get that from the difference between the position of the object x and the position of the observer xe. We can turn that into some angular coordinates that are varying as a function of time. The observer positions we know very well. We know where the TESS spacecraft is as a function of time. And then for the position of the object, we're going to substitute in that alpha, beta, gamma expression that I showed before to say, okay, this is what we expect the observed position in any given exposure to be as a function of time. And so that's dependent on the initial orbital state that we've chosen and the position of the observer. Okay, so this isn't anything different from saying that for any given orbit, we know where it's going to be. But one quick aside is that you can invert that expression to say that, well, the starting position in the first frame is a function of the observed positions at the observed times and some other chosen parameters. And what that means is that you're mapping all of the flux from a whole bunch of different exposure positions at a whole bunch of different times back to one position at one time. And that's just shift and stack. So this is the mathematical expression of shift and stack. But anyway, coming back to these pixelated discrete sets of orbital positions and velocities, we want to think about, okay, we're going to chop them up. We're not going to choose all possible orbits, we're just going to choose discrete sets of them. So how many orbits are we going to choose, and what does that mean in terms of the total number of computations that we're going to have to perform? Okay, so what we need to consider is the total number of computational operations that we need to consider that we're going to need to perform in order to exhaustively search everything. We're going to need to consider the total number of sectors, the total number of exposures per sector, the total number of pixels on each exposure, the total number of those angular velocity bins that I talked about, and also we need to consider the total number of radial distance bins, like the total number of distances that we'll want to search for these objects at. And I don't have time to go through each of these components, but one can work out relatively easily expressions for each of these components. Some of them are just fixed numbers, like the number of sectors we need to consider. Here, I've got 26, a little out of date, but obviously it's going to change things by a factor of a couple. But the main things to see are that there are some strong dependencies on the total time span of the observations that you're considering. So here, about 27 days for a sector. And strong dependencies on the pixel scale and on the distance that one wants to search. And then the total number of exposures and the number of pixels as well. Now, it turns out that when that study by Bernstein et al. Using HST that I mentioned earlier, when they performed this study using this approach, they need to perform about 10 to the 16 operations. And it turns out that coincidentally, TESS, searching all of TESS data, will also take about 10 to the 16 operations. And it's the reason that they end up being the same is so TESS pixels are huge compared to HST pixels. So that makes TESS data really easy to search in comparison. And whereas the HST data was searching just on a much shorter, sort of around about 1 day time span, and they had many fewer exposures, around 50. And so it sort of works out weirdly that like the order of magnitude number of calculations that need to be performed to search the outer solar system is pretty much the same. But the Bernstein study was done back in 2004, and they did it successfully, exhaustively searched. And the cost of like computational operations is now somewhere around about 1,000 times cheaper. So it is going to be trivially easy to search the TESS data now compared to what it was like back in 2004. Okay, so let's turn now to consider what can be realistically detected using TESS data. So after the first 2 years of the nominal mission and then the first subsequent 2 years of the extended mission, we expect that TESS will have observed somewhere in the region of 94% of the sky. And we're going to want to take a sector's worth of data, so over 1,200 exposures, and stack those up and try to discover faint objects. So if we're doing that, the relevant limit that we need to consider down at the faint end is that zodiacal noise and read noise are the dominant contributions to the noise at that level. So we can model the noise using an expression as displayed on the screen, where you've got the source component, the zodiacal component, and the read component. And so we can get our overall noise contribution. And then we can take that and we can put it into a detection efficiency calculation that says what's the expected signal to noise ratio for a given object of a given magnitude, and let's compare that to some significance with which we want to detect things. So we might want to detect things at a 5 sigma level, something like that. If we assume that, then we can make a model of what our expected detection efficiency is as a function of object magnitude. So here we're stacking up somewhere in the region of 1,200 or 1,300 exposures, i.e. from an entire sector. We're saying that we've got a high amount of zodiacal contamination. And then if we do that, for objects that are around 21st magnitude or so, we're going to be able to detect those with almost 100% efficiency. And then as the objects get fainter, by the time we get down to around 22nd magnitude, we've dropped down to about 50% detection efficiency. So even in a fairly conservative limit, we're going to be able to detect 22nd magnitude objects. Pushing on a little more optimistically, if the zodiacal light is low, we may be able to get out somewhere around another half a magnitude out of it, push down towards 22.5. Now, obviously, some areas of the sky may have bad zodiacal contamination, additional contributing effects, and so obviously that will push things in the opposite direction, make our faint limit a little brighter. But one thing to emphasize is that for these objects that I'm showing here, known objects that we've measured using TESS data, right, where both our group and the Rice and Laughlin group have independently measured these objects, and we all agree that these objects have a signal to noise ratio that is much more in line with the low zodiacal contamination limit. So i.e. there are at least some regions of the sky in which contamination is low, and we can get down to detection efficiencies of 50% at around about the 22.5 magnitude level. So this is thoroughly enthused. To calculate our expected yield from shifting and stacking the TESS data, we need to consider the expected distribution of outer solar system objects on the sky. So Kuiper belt objects are concentrated close to the ecliptic. The majority of them are within plus or minus 12 degrees, giving you an effective area of 8,600 square degrees around the ecliptic, whereas the centaurs and scatter disk objects, while they're more poorly constrained, it's certainly a much broader distribution over a much larger area of the sky. So we need to consider that in conjunction with the fraction of the sky that TESS is expected to observe close to the ecliptic. And so we think for the area of the Kuiper Belt objects that TESS should observe somewhere around about 7,000 square degrees out of that 8,600 effective area. And then similarly for the centaurs, TESS will observe something around about 15,000 square degrees out of the effective area of like 17,000 degrees for the total population. So that gives us the fraction of these populations that we expect to observe, and so then we need to consider the expected sky plane density of objects as a function of magnitude. So when we do this for the Kuiper Belt objects, we find that TESS should be able to observe around about 1,400 Kuiper Belt objects that are brighter than 20-second magnitude. And then similarly for the centaur and scatter disk objects, we predict that TESS should be able to observe around about 1,600 objects brighter than 20-second magnitude. As I'm just reminding you, on this semi-major axis eccentricity plot, these centaurs and scattered disk objects that I'm considering sort of as one unit, about 1,600 of those, and around about 1,400 Kuiper Belt objects. However, the thing to remember is that we actually already know of about 1,200 KBOs that are brighter than 20-second magnitude already. So that means that TESS is likely to only be observing a couple of hundred new things, give or take. In contrast, for these centaur and scatter disk objects, there's only about 800 of those known at present. And so with a predicted yield of somewhere around 1,600 for TESS, this means that we're effectively doubling the size of the known population. And so we're likely to be able to start to significantly constrain the spatial density and number distribution of these objects. And this really sort of points out, highlights the power of having an all-sky survey that you can push down to 20-second magnitude, because the majority of data that we have at the moment on TNOs tends to come from ground-based surveys that concentrate fairly close to the ecliptic, so they're good at picking up the Kuiper Belt objects, but relatively poor at getting these scattered disk objects and centaurs that cover a much larger fraction of the sky. In addition to surveying the outer solar system, one can also search for other populations. So we saw that somewhere in the order of like 10 to the 16 operations are required for an outer solar system search. But as part of doing that, we saw that the number of computations that are required scales with the distance to the power minus 4. So if you want to search for populations sort of in the inner solar system, say as distance goes towards 3AU, the asteroid belt, then naively the number of operations required to do a full shift and stack survey down to the 20-second magnitude are going to go towards like 10 to the 20 operations. So that's probably a little on the high side for it to be practically realizable. But we don't have to go down to 20-second magnitude. There are interesting populations such as interstellar objects, which can be significantly brighter. So Oumuamua was somewhere down the 21st, 22nd magnitude sort of level, but Comet Borisov was around 18th, 17th magnitude. So one could undertake an all-sky survey down to 18th, 19th, 20th magnitude, just stacking a few tens of images. And in that scenario, then the number of operations you require to perform that survey are somewhere in the region of like 10 to the 17. So that's eminently possible. And so we have a side project ongoing to start looking at that. Okay, so now I'll finish off by highlighting some work to practically implement these shift and stack techniques on TESS data. So around about a year ago, Milena Rice and Greg Laughlin put a paper out in which they in detail examine data from sectors 18 and 19. And they're primarily using that data to search for Planet 9 candidates, so distant objects and the orbits of which are so slowly moving that the objects will basically execute straight line motion in the field of view once you've taken out the motion of the observatory. And they find that they can definitely get down to 20-second magnitude in many areas of the sky, slightly deeper in some, and in some areas of the sky it's not quite as good due to the sort of complexities of dealing with some varying background subtraction, high background contaminations in areas near the galactic plane, obviously. But in general, they demonstrate that this method is entirely applicable and successful when applied to TESS data. So in parallel with that, I've been working with postdoc Mike Alexanderson and Matt Holman and to develop some public code to implement this shift and stack technique. So we've demonstrated as a sort of proof of principle that we can get down to 20-second magnitude for some known objects. So I've shown these plots earlier before, detections of Sedna, 2015 BP519 and 2015 BM518. Andras Powell demonstrated that he could get those using one pipeline, and Mike Alexanderson has sort of reconfirmed that using a new version of the shift and stack software that we've developed. And so now we're concentrating on developing some easy-to-use software that can do the shift and stack data in just a handful of lines of code. So here I'm showing doing shift and stack for a known object, and here it's operating on some Subaru data. And so in just something like 10 lines of code, we can get data imported, shifted and stacked, and plotted. And you can clearly see the object is easily detected there in this image. And I'm sort of highlighting this particular piece of code to deliberately emphasize that we're developing software that is going to be applicable to any observatory, including TESS, and is going to be available to the community to shift and stack whatever data source they're interested in. So in summary, we have this key project that's been funded to shift and stack TESS data to search for distant outer solar system objects. We predict that the scientific yield is likely to be hundreds of Kuiper belt objects, centaurs, and scattered disk objects. And it's going to be particularly scientifically important for these highly scattered populations like the centaurs and the scattered disk objects. And we're developing code to do this analysis, and it will be released to the public. And then we also have some ongoing projects in parallel with this, in which we're trying to use the same techniques to discover interstellar objects. Okay, thank you very much.